Okay, so the next topic of this section, so we're still in 3.2, is the concept of unit vectors. What are unit vectors? Unit because they are vectors of length 1. One. Okay. So, for example, in 2 space, vectors are of length 1 are all the vectors that end up on the unit circle, because the unit circle is the circle of radius 1, and a circle, of course, centered at the origin. So all these vectors are vectors of length 1. It's not too hard to understand that the coordinates of these vectors would be of the form cos theta, sine theta, right? So that's one thing. So in 3 space, those vectors would end up at a point on a unit sphere. Okay. Now, maybe let's consider something. Imagine I've got a vector u, okay, I don't know, with coordinates, I don't know, I'm creating numbers here, 1, 2, minus 3, okay, so that's vector u. I could easily calculate its length, its norm, so that would be square root of 1 plus 4 plus 9, so that's square root of 14. And imagine now, and in some situations we'll want to do that, we'll want to create a vector that is maybe 3 times as long. So here, okay, let's erase this. Maybe let's start with something a bit bigger. I want to create one that's 3 times as long. Well, actually, this one looks twice as long. So maybe I'll just write twice as long, 2u. Or maybe I want to create a vector that's, I don't know, half as long, but pointing in the other direction. Maybe that's too long for half, like this. That's, well, I should write minus a half of u, right? Because it's pointing in the opposite direction. My question is, what are the lengths of these vectors? How, and more specifically, can I, here's a general question, can I come up with a formula if I multiply u by some scalar? Remember, a k is usually used for scalars. So here my scalars could be 2, could be minus a half. So if I scale it, how is the length of this new vector related to the length of u? So obviously there's something missing, right? Those lengths are not equal, so there's something I have to fill in here. And what is that? Well, if I'm looking at 2u, how is its length connected to the length of u? Try to answer that. Well, it's twice as long, so it should be twice the length, right? 2 times the length. But if I have minus a half of u, okay, you might be tempted just to put minus a half here, but that doesn't make sense. This lengths are always positive, so this is a positive quantity. This is a positive quantity because that's a length. So I can't multiply by a negative, because on the right hand side I have a negative times a positive. So what's the right quantity? It's not minus a half. How would I change this? Well, I think you got it, right? So it's plus a half I should put here, right? It's so this vector minus a half of u, it has the same length as the vector 1/2 of u. They have the same length, so it's 1/2 times the length of u. So what's the general formula here? So you can see it doesn't work if the number here, if I put the same number over here, they're not the same, right? For minus a half I need a half, But for 2, it's the same number. For 2, it's 2. So what expression gives me, in general, what I need? If I have k here, k could be positive, could be negative. What would I put there? And if you thought about your Sec 5 or maybe your Cal 1, maybe you've deduced that this should be the absolute value of k that goes there. So this is maybe something to remember. The norm of k times u is absolute value of k times the norm of u. So I'll leave you maybe as an exercise. Try to prove this algebraically. So exercise, prove the result algebraically. Because someone could come and say, oh, well, all your reasoning works in 2D, but what if I'm in 4 space? Maybe things behave differently in 4 space. So can you come up with a proof of this result independently of how many coordinates there are for you? Actually, here we're in 3 space because I used 3 coordinates for you, 1, 2, and -3. But regardless, okay, I'm telling you this result works in any space. Try to prove this. Maybe start your proof like this. Let u be the vector with general coordinates u1, u2, u3, un. Okay, and how do we prove a statement like this? You start with the simplest side. So this is the simplest side here. Try and end up with the other side. So you're gonna in your proof you're gonna write norm of ku, and you're gonna write explicitly what this is. Well, maybe I'll do that first step for you. Maybe we can write it here. So if u is this, then ku will be k times u is what do we get by multiplying each coordinates by k, each coordinate by k. So when I calculate the norm, I'm going to do k u1 squared plus k u2 squared all the way to k un squared. And our goal is to write down equivalent expressions until we get absolute value of k times norm of u, times the norm of u. So what is that? Norm of u, maybe you can write it explicitly just to see what our target is. This is where we want to end up. We want to end up with this expression, absolute value of k times the square root of u1 squared plus u2 squared all the way to un squared. So in some way we want to pull out the k from the expression I wrote initially. Okay, so there are 2 things you're going to do to pull out the k. And one thing to remember, eventually you're going to have k squared and you're going to want to take the square root of it. Okay, and something to remember is that this is exactly the absolute value of k. So when you take square root of k squared, usually students, they write k because they kind of cross out the square with the square root, and that only works with positive numbers. But if you've got negative numbers, you're going to end up with the opposite of k. So you're going to end up with its absolute value. So this is something from Cal. I don't recall seeing this in high school personally, but definitely we see it in Cal 1. Root of k squared is equal to k. So try to fill in. So maybe there are a few steps missing here. Try to fill in the details of the proof. Okay, coming back to our initial problem, initial topic, we're dealing with, we want to work with unit vectors. So one problem I want to solve is, given this vector u, and maybe we can work with the example I just wrote before. So u is 1, 2, minus 3. I'd like to create actually, and I'm just going to erase some stuff to make space, but I'd like to create, I don't really care so much about this vector in red here, but I'd like to create a vector that's of length 1. So u here, you can check it has definitely a length that's larger than 1. Well, actually we did check it. Its length is root of 14. So I'd like to create a vector that's pointing in the same direction as u, but of length 1. And eventually I'll also want to create a vector that's opposite of length 1. But that's easy. Once I've got a vector in the same direction of length 1, I just take the opposite of that vector and I'm done. So maybe a problem. So I'm given u, which is the vector, what did I say, 1, 2, minus 3. Compute a vector of length 1, or I could have written down a unit vector, okay. Compute a vector of length 1 pointing in the same direction as u. So how do I do this? Well, if it's going to be pointing in the same direction, it's going to be proportional to u. So it's going to be sum k times u. So if I've got u, the unit vector I'm looking for is sum k times u, but I need to choose my k wisely. Okay. So what do we want here? I want the norm. I want to choose k so that it's the norm of ku is going to be 1. So this is what we want. I want that k to be such that it satisfies this equality. Now, based on our previous result, this is this is absolute value of k times norm of u, and that should be equal to 1. So I'm going to solve for k. So the absolute value of k is 1 over norm of u. So there are two values for k, two possible values. It could be plus or minus 1 over norm of u. But 1 over norm of u, that's a positive quantity. So if I want it to be pointing in the same direction, I want to choose the positive value. So therefore, here, k equals 1 over norm of u because it's pointing in the same direction, since ku is pointing in the same direction. Okay, so therefore the vector I'm looking for, so the vector is 1 over the norm of u, so that's our k, right, times u. 1 over the norm is 1 over root of 14, and u is 1, 2, minus 3. I could keep it like that, or if you prefer, you can also write it like that. Both are just as good. And we're not necessarily going to rationalize the denominator. You can keep it like that. Okay. If I want to create one that's pointing in the opposite direction, the unit vector pointing, well, by the way, we're done, right? Answering the question I just asked initially, but let's say I add another one, the unit vector pointing, unit vector pointing in the opposite direction. Well, all you have to do is take the opposite of the previous vector. So the unit vector pointing in the opposite direction is minus 1 over the norm times u. So it's going to be, I'm not going to rewrite everything, but it's going to be the opposite of the previous vector. So given a vector, you always have two unit vectors associated to it, one pointing in the same direction, which is 1 over the norm times the vector itself, and minus 1 over the norm times the vector is the one pointing in the opposite direction. So that's something to remember. Maybe a final little problem to work on. So given v, which is 3, 5, minus 2, find a vector of length 6 pointing in the opposite direction. So now it's not a unit vector I'm looking for, it's a vector of length 6. So how are we going to solve this? Well, we've got our v. I want one pointing in the opposite direction of length 6, right? So, and it's not 6 times v, right? I'm looking for, so of length 6 in total. So so this is not going to be v at all, right? So it's going to be some multiple of v, and this should have length 6. So this is the problem I'm trying to solve. So how can we solve this? One good technique is to use unit vectors. So I'm going to create a unit vector of length 1 that's opposite to vector v, and then I'm going to multiply that vector by 6 so that it has a length of 6. So let's do that. So so I'm going to create the vector, a unit vector that's opposite to v. Okay, so that's the one, and I'm going to multiply it by 6. So overall, let me, before doing any computation, you can simplify it like this. So you see that instead of having -1 at the top, you have minus the value of the length of the vector you're looking for. So if it would have been a vector of length 7 pointing in the same direction as v, would have been 7 over the norm times v. So this I can do easily. So it's -6. What's the norm of v? So that's 9 plus 25 plus 4 square rooted times v. So that's -6 over this is root of 38 times 3, 5 minus 2. Okay, there's not a nice perfect square that's a multiple of 38, so I can't really nicely simplify to square root of 38 here. So I can just leave it like my answer like that, or of course you can always write it up like this. This is also valid, and usually we don't rationalize the denominator, just keep our answer like this. So maybe one thing about simplifying square root. So let's say you have something like this, square root of 28. Can always simplify it because in 28 lies a perfect square. For 28 is 4 times 7, and 4 is a perfect square. So this is the same as root of 4 times 7, and the square root of product is the product of the square roots. So you see the square root of 4, that's 2. So you can actually simplify that square root and pull out a 2 out of it. But I can't do that with 38 because 38, there are no perfect square that are that divide easily 38. So if, 1 is useless, but 4, 9, 16, you see those are not factors of 38. So I'm just going to leave 38 the way it is.